Hi everyone. What we're going to talk about today is when a function is not differentiable at a particular point. And we've probably already done a little bit of work around this that you do remember. So first of all, a function is not differentiable at A if it's not continuous at A. For example, if we have something like this, a little piecewise function, it would not be differentiable there. Okay. For part B, if we have a corner or a cusp, okay, so for example, if we have something that looks like this, like say an absolute value right here at A, we would not be able to differentiate at that value. Same thing if we have some kind of a cusp, okay, so we would not be able to find the derivative at that particular point. And also if it has a vertical tangent, okay, so a vertical tangent line looks something like this. We have some functions that look like this with a tangent line that's vertical. So that would be another example when we could not differentiate at that particular value. Okay, but most of the time we can, and that's what we're going to focus on. So let's take a look at this function, and we'll kind of work through what we just talked about. So what I'm asking you to find is if the function is differentiable at x equals 2. So the first thing we should probably check is this function continuous at x equals 2? So typically what I do is I set these two values equal to each other and I drop the 2 in. So 2 squared minus 2, is it equal to 4 times 2 minus 6? So that's what we're checking there. 2 squared is 4, 4 minus 2 is 2, 4 by 2 is 8, minus 6 is 2. So it is continuous, and now what we can do is we can move on and see if the slopes of the tangent lines as we approach 2 from the left and 2 from the right are actually equal to each other. And we'll graph this when we get there. We'll graph it in a moment. But let's go ahead and let's look at, we're going to take the limit. Oops, I'm in that pen again. Let's not do that. The limit as h approaches 0 from the left side. So we're working with this right here. Okay, so of f of a plus h minus f of a, all divided by h. So that's going to look like a squared plus 2ah plus h squared minus 2 minus a squared minus 2, all divided by h. And of course, we know we have to take this negative and distribute it in. Positive 2 and negative 2 cancel each other out. Negative a squared, positive a squared cancel each other out, leaving us with the limit as h approaches 0 from the left side of 2ah plus h squared over h. We should all know where this is going. These cancel, this leaves us with h to the first. And when we substitute 0 in, we get 2a. Now, we're checking at the point x equals 2. We want to know, are the slopes of the tangent lines equal? So we will take f prime of 2. Basically, we're going to take 2 and substitute it in to what we found to be the slope of the tangent line for x squared minus 2. So 2 times 2, which is 4. So that is the slope of the tangent line from the left. Give ourselves some little notes here. Okay, next we're going to do the same thing, but we'll be working from the right. So same idea though. We're going to take the limit as h approaches 0 from the right. And remember, our function is 4x minus 6. So we will have 4 times a plus h minus 6 minus parentheses or brackets 4x minus 6 all divided by h. And we'll clean this up. I'm just going to do it right here. 4a plus 4h make this plus a negative and a positive. And if you take a look, of course, our positive 6 and our negative 6 cancel out. Oh, it looks like I made this one an x by accident. Negative 4a and positive 4a cancel out. So we are left with the limit as h approaches 0 from the right. We're taking the right-sided limit of 4h. That's it. Everything else canceled out. Oops, sorry, over h. Of course, these reduce, and we're left with 4, which is the slope of the tangent line from the right. So we had continuity as we found up here, and now what we can see is that the limit from the left is equal to the limit from the right, whoops, as we approach 2. Therefore, it is differentiable at x equals 2. Okay, it is differentiable. Let's take a look at this, okay? I do want to scroll back up and graph it because I think graphing it will be a little bit helpful also. We certainly need to know how to do all the work, but when we graph this, so first of all, I kind of like to make a little light barrier at 2 so I don't go past that. That's where the domain is separated. And this first function is x squared minus 2. Well, we know that's a parabola that's been translated down 2 units and has the standard size, right? The same size as the parent function. So 1, 2, 3, open circle right there. This is what our function looks like. Our second function is the line 4x minus 6. So we can go 4 times 2 because we're starting at 2. Our domain starts at 2. 4 times 2 is 8. Minus 6 is 2. And we have a slope of 4. 1, 2, 3, 4 over 1. Or down 2, 3, 4 would have brought us left over here, which is out of our domain. But look at what we have here. Okay, so the slope of these tangent lines is equal. In fact, this is the tangent line at, oops, I cut through, at 2, x equals 2. Okay, let's go through, let's do the next one. So the next one I'm asking you if this function is differentiable at x equals 1. So again, I like to check for continuity first. Okay, so we'll check for continuity first. So we want to set these two values equal to each other when x equals 1. And that'll let us know if we have jump continuity or what we have going on there. So we have 1 cubed plus 2. And we want to know, is that equal to 3 times 1 minus 2? This is our big question. 1 plus 2 is 3. 3 minus 2 is 1. These are not equal. This function has a height of 3 when x equals 1. So 1, 1, 2, 3. It will end there. But the next function starts at a height of 1. So because we have jump discontinuity, this function, so f of x, is not differentiable at x equals 1. Okay? And again, if it's not continuous, we can't differentiate at that particular x value. We could at other points, but not there. All right, so let's check the last one. And what we're going to do is the first thing I do like to check for is continuity. So again, we're at x equals 1 for this function. So we're going to set negative 1 squared plus 3 equal to negative 2 times 1 plus 4. Let's see if it's continuous. So 1 squared is 1, negative 1 plus 3 is 2. Negative 2 plus 4 is 2. That means it's continuous. So we've kind of satisfied the first condition And now what we'll do is we'll take our left and right-sided limits. So our left limit is right here. So we will take the limit as h approaches 0 from the left. It's a left-sided limit of negative a squared plus 2h plus h squared plus 3 minus negative a squared plus 3, all divided by h. Okay, let's go ahead and apply our negatives. Let's see what we have here. So we have plus, this becomes negative, negative, negative. This becomes positive, and this becomes negative. The 3's are gone. A squared and negative a squared cancel each other out. This leaves us with limit as h approaches 0 from the left of negative 2ah minus h squared over h. And of course, we can cancel h right here. We are left with, now when we drop that 0 in, negative 2a. Okay, and now let's find the slope. So let's find the slope of the tangent line when x equals 1. So we have negative 2 times 1, which is negative 2. Okay, so let's keep that, because if the slope of the tangent line here is negative 2, then the function is differentiable at x equals 1. If it's anything besides negative 2, it's not differentiable. So we will take the limit as h approaches 0. We're doing a right-sided limit of negative 2a plus h plus 4 minus, and then in parentheses, negative 2a plus 4, all divided by h. And just to save a little time here, I'll do this right here, negative 2a minus 2h. We will apply this negative, and let's see what happens. Negative 4 and positive 4 cancel each other out. 2a and negative 2a cancel each other out, leaving us with the limit as h approaches 0 from the right to be negative 2h over h, which is negative 2. And notice there's no variable there, so there's nothing to substitute in. Look at this. The limit from the left is equal to the limit from the right as x approaches 2, right? As x approaches 2 from the left and from the right. It is continuous, therefore it is differentiable running out of space at x equals 1. And let's go and look at what these functions would look like on our graph too. Let's take a look at that. That's always helpful. So let's graph our first function. So it's negative x squared plus 3. So we know it's a function that's going to be reflected. It's a parabola that's going to be reflected, and it rises up 3 units. So 1, 2, 3. And then, of course, it's the same width as our parent function. So it's going to look like this. Notice that it goes up to and includes 1 for the domain. So we'll have a closed circle here. This is our first function. And our second one, negative 2x plus 4. So negative 2 times 1 is negative 2, plus 4 is 2. So that shows the continuity. And then the slope is negative 2. So down 2, right 1, down 2, right 1, down 2, right 1. We could do that all day. And it looks like this. So there really is no corner or cusp. Even though it went from being a parabola to being a line, it was just the right slope at that point to not create a corner or a cusp. and therefore it is differentiable at x equals 1.